So Laplace transform is what we're looking at. Okay, we might have heard about these transforms: Z transform, Fourier series, discrete Fourier transform, cosine transforms. But what is the necessity of learning all these transforms? What is this transform doing actually? Is what one needs to understand. Okay, what they do is, see, whatever we do, natural domain. Let's call as natural domain. What is natural domain? What is natural domain? Natural domain is uh, the voice signal is in natural domain. Okay, then you can say image what you see. If you see a image from your eyes, that's in natural domain. Okay, if you see a video, if you see anything, we can say that comes in natural domain. Okay, then what we can say, speech we have taken, that is voice signal, image we have taken, video, they're all natural domains. What are natural domains? It's actually whatever you can sense or feel in the nature, they're all in natural domain. What is that natural domain? That is time domain. Natural domain is time domain. Understand? Why do we need these transforms then? What these transforms do on time domain, they're all signals. Okay, signals are generally represented as say x of t, because it is time domain, right? So time here is t here is time. Understand that? See, t is time, then x is signal. Okay, so x of t is what? X of t is time domain signal. Everybody understand? X of t is time domain signal. Okay, so this time domain signal is in natural domain. Natural domain is time domain. Whatever you are listening to, okay, whatever is soon after we switch on the fan, a wind blows, right? So that is also in term domain. We can plot that. Why we can call them all as time domain signals? This signal means, first of all, understand this we'll be taking in more detail in signals and systems next semester, in fourth semester. But here, unless you understand what is a signal, it will be difficult to understand why we should go for transforming a signal using different transforms. Okay, why we need to transform is, see, not everybody's voice is the same. Okay, I've been telling you that I have not seen you and you have not seen me. Okay, but even then you've heard me for such a long time, for months together you've heard me. What does that mean? Even without looking into me, if sometimes somebody plays my voice, you'll understand, okay, it is his voice, it is Sunil's voice. You can easily make out. Okay, and if you take somebody else's voice, you can easily make out the difference in the voice, how they sound. For example, if you take cricket commentary, in cricket commentary, what do we do? Suppose there are no TVs. Take the days when there were no TVs and you're made to listen to the commentary only in the radio. Understand? What do you do there? You the match is on and you keep listening to the commentary, and you will have all the interest to listen to the commentary because you're not able to see. Okay, so who are the commentators? You know Sunil Gavaskar, you know Ravi Shastri, you know Harsha Bogle, Sanjay Manjrekar nowadays, isn't it? Now, without seeing them, people can make out, okay, it is Sunil Gavaskar's voice or Ravi Shastri's voice, isn't it? So that is because each voice is unique. each voice is unique. That's why not everybody's voice sound the same. Why? Because frequency components in the voice. What is a signal? Signal is a frequencies. Okay, set of frequencies. Okay, frequency components are not the same. Not the same. Okay, so we can understand why the sound differs from person to person, means why the voice differs means the not all the frequency components in all the voices are same. Different frequencies will have different voices will have different frequencies. What is audible range? What is audible range? Audible range is, everybody understand this, audible range of the voice signal. Anybody if you have heard? It's 20 hertz to 20 kilohertz, they say. Okay, audible range of frequencies. In this range you can listen to the frequency. Maybe human ears are not good enough to listen to this, and they are not good enough to create this also, to generate this particular frequency also. So if you take voice frequencies, voice means human voice, understand? Okay, voice frequency range, if you take, okay, it is up to 4 kilohertz, not beyond that. Maybe it starts from 20 hertz, you see. It starts from minimum 20 hertz and goes till 4 kilohertz. Beyond 4 kilohertz, one cannot generate the signal. Okay, any human voice you take anybody's voice for that matter. Okay, the frequency components would not go beyond this. Yes, the male voice and female voice would differ. What way they would differ? In male voice, you have something called as bass. Okay, here you have something called as treble, treble, bass. What is bass? Boom, boom, boom. If you are able to listen to the sound, boom, boom. If you bass jastima, if you're good enough with if you have experienced this with musical systems, the speakers rather. Okay, so there you will have adjustment to make bass more or treble more. Get that point? So bass is more in male voice. Okay, female voice has more treble. Okay, where there is more treble, it's high frequency signal. It's high frequency signal. Where bass we say comparatively low. Comparatively low frequency. Male voice. Understand that? Okay, maybe this female voice would be near 4 kilohertz, or male voice could be near 3.5 kilohertz, the dominating frequency components. They'll have all the frequency components ranging from say 20 hertz to 4 kilohertz. Okay, but which components are more in number? That would decide the voice. Okay, so it is less for male voice, it is more for female voice, because their voice is sharp. We can call the female voice as sharper compared to the male voice. Okay, where will you get all this information about frequency? Where will you get all this information about frequency? See here, suppose if you record the voice that I'm delivering a speech, right? So if you record that and if you plot it, it looks like something like this. What is that? So this is amplitude, you say, signal amplitude. Okay, and this is time. With respect to time, this signal x of t, which is voice signal, is varying with respect to time. Here I'll be less louder. Okay, my frequency components are differing. Suddenly I increase my what? Loudness. Okay, now there are different frequency components. Okay, so where will you get the frequency information? Now I cannot say seeing this signal, I cannot say what? Seeing this signal, I cannot say that, okay, 4 kilohertz components are more in number, or I cannot say 3.5 kilohertz components are more in number. I cannot say that. So what do I need to do on this if I have to understand that frequency information? I have to apply transform on this. Apply transform. So when you apply transform on time domain signal x of t, what you will get? You will get a frequency domain signal, say x of s, x of jw, okay, or say f of s. They're all different transforms. They're all frequency domain components. Okay, here you can get the frequency information which is not available in time domain. Understand that? Why do we need to apply transform on time domain signals? We have to apply transform on time domain signals to fetch the frequency information of the signal which is not available in time domain. Seeing this time domain signal, I will not be able to say which components are there. What I can say, rather, this is a speech, okay, which is what are the characteristics we can understand seeing this is continuous in time. Okay, this is continuous in time, we can understand. I'm not giving a big pause, I'm continuously speaking. Continuous time, and it is non-periodic. Why it is non-periodic? What is periodic? Periodic is the signal which keeps repeating itself. For example, if you take sine wave, if you take sine wave like this, okay, this is periodic. Why? See here, after every, say suppose this is 0, 1, 2, 3, 4, these are all seconds, t in seconds. Okay, this is x of t rather. Fine. What is happening to this sine wave? See, from 0 to 2, there is a pattern. Okay, and the same pattern is there from 2 to 4. So that means it is repetitive in nature. So the signal which is repetitive in nature are called as periodic signals, but our voice is not, the speech is not periodic in signal. It is non-periodic. Okay, so can't we generate a periodic wave? Yes, we can generate. How? What would be periodic if I speak? See, if I chant some mantra, say Om Namah Shivaya, Om Namah Shivaya, Om Namah Shivaya. What's happening? Om Namah Shivaya is repeating after, say, every 1 second. Then it would become periodic. But if you take speech, we don't keep saying the same after every particular after every some say few seconds, some particular duration. Okay, so that's why speech is considered as non-periodic signal. See, it is non-periodic. Understand that? Now, why I'm saying the speech signal is non-periodic, which are periodic signals, which are discrete time signals. Okay, to understand this, we have to learn signals and systems, but we have so many different transforms, right? So many different transforms. Okay, so Z transforms are there, Laplace transforms are there, Fourier transforms are there, discrete Fourier transforms are there. Not all the transforms are applicable to all the signals. Understand that? There are different types of signals. As I said, there are different types of signals, which are those continuous time signals x of t. Then say discrete time signal x of t. Then say periodic signal. Okay, then we can say non-periodic signal. Okay, so there are different types of signal. Not all the signals are suitable, okay, when it comes to application of these transforms. Not all the transforms are applicable to all the signals. Okay, so this Laplace transform is applicable to continuous time signal. Understand this? This is applicable to continuous time signal. Z transform is applicable to discrete time signal. Discrete time signal, which you'll be studying in the next semester. Fourier transforms are applicable to continuous time non-periodic. Fourier series is applicable to continuous time periodic. Discrete Fourier transform is applicable to discrete signals. Okay, but when it is non-periodic. So different transforms are used for different signals, but the purpose is what? Purpose is to fetch the frequency information in the signal. That's why these transforms are used to transform a time domain signal into frequency domain. All the transforms are meant for this. Why? To extract frequency information, which is not available in time domain. Not available in time domain. Understand that? So this is the introduction regarding the transforms. Now, in particular, the transform that we are considering, okay, the transform that is there in your syllabus is Laplace transform. Okay, so everybody just take this. The transform that we are considering is Laplace transform. Okay. So I've told you Laplace transforms are applicable for what? What? They are applicable for all types of the signals. No, they are applicable only for continuous time signals. How do we represent them? Continuous time signals are represented as x of t. Understand? So what you'll have is, if you have x of t, what you would do? You would apply what? Laplace transform on this, which is LT. So if you apply Laplace transform on x of t, what you would get? What you would get? You would get, say, f of yes, or say x of yes. You will get, since it is x of t, here it is capital X of yes. Then you can ask me, where is that frequency? Where is that frequency? Yes is what? It is sigma plus j omega. We call them as complex frequencies. They are frequencies only, but they are not directly represented in terms of the frequency omega or f. Okay, it is represented in terms of yes. Okay, which is complex in nature, like this, sigma plus j omega. So this is one way. So how to represent the application of, see here, what is x of s? X of s is obtained when you apply Laplace transform on x of t. We can say like this. Understand that? Okay. So what is x of s? X of s is obtained when you apply Laplace transform on x of t. This is one way of representation. Or we can represent the same as x of t, bidirectional arrow, write LT here, then say x of s. What is the meaning of this? If you have x of t in hand, you can apply Laplace transform on it to get x of s. Or if you have x of s in hand, you can obtain x of t by applying inverse Laplace transform. Understand? We can apply inverse Laplace transform. Okay, x of s is there, means we apply inverse Laplace transform to obtain this. If we have x of t, we apply Laplace transform to obtain x of s. Okay, so this x of t and x of s are called transform pairs. They are called transform pairs. Understand this? Now we shall see how the equation looks like. Equation for Laplace transform. Everybody just take this equation for Laplace transform. Okay, now how does it look like? So it looks like this. What is that? If you have f of t, okay, so if you have f of t and if you apply Laplace transform on this, what you would obtain? You would obtain f of, yes, if you have f of t, you will obtain f of s. If you have x of t, you will obtain x of s, capital X of s. That's it. Okay, I'm taking f of t, so it is capital F. If I take x of t, okay, then it is capital X of s. That's it, nothing much. Fine. So it is given by 0 to infinity f of t e power minus st dt. Maybe you have done this in your mathematics. I don't know, M1, M2 you had, or M3 you're learning, or in M4 you'll be learning all this. But you will be seeing this, or you already have seen this transform in your mathematics. Okay, but there you'll just be learning the output of an application. Here, from the point of engineering, you'll not see these transforms. Okay, from the point of engineering, if you see, okay, engineering, we'll be applying transform on the signals, whereas in mathematics you're applying transform on some set of numbers. Yes, so what we do is we change the approach. We change the approach of learning the transforms. What way? In mathematics, we don't take it as engineering application. It is application on some set of numbers. But here, when it comes to electronics engineering, we are looking at signals, and on the signals, you are applying the transforms. We have different types of signals. We have seen different types of transform, and we have seen different types of signals. And in that, we'll be seeing some basic signals. Okay, so we shall go now. Okay, this is what is the transform equation looks like. F of t is time domain signal, f of s is frequency domain signal, or they just call it as Laplace domain. Since directly the frequency is not there, they call it as Laplace domain or s domain. Understand that? Why it is not going from minus infinity to plus infinity? If it is going from minus infinity to plus infinity, it is called as bipolar transform. Bipolar transform. But for the engineering applications, maybe if you consider the applications wherein the circuit applications, if you take electronics and circuit applications, you have circuits rig up. There we don't go with minus infinity. We go from 0 to infinity. So this is unipolar. On one side you have. So this is 0 to infinity means it is unipolar. See, if this you are seeing, right? If it goes from minus infinity to plus infinity, it is bipolar transform. But in circuit applications, this will not be the case. Okay, so what is this? 0 to infinity. So if you have 0 to infinity, it is called as unipolar transform. What is bipolar there? Bipolar means both minus infinity to 0 and 0 to infinity. Okay, so it is bipolar. Negatives also are considered, the positive time is also considered, but here no, it is only positive time is considered. That's why it is unipolar transform. What we have considered here is for circuit applications. Everybody understand that? Now we shall just see what type of f of t's which are we can consider here. F of t's, as I told you, this is in time domain. Okay, this is in Laplace domain, let's say Laplace or yes domain. We can say frequency domain, okay, but sometimes they don't want to call it as frequency domain because frequency is not directly there. Frequency is hidden like this in complex form. Okay, so that's why it is better we refer to it as Laplace domain. Everybody is okay with that? See here, when you take f of t now, when you take f of t, we can first see f of t as a basic signal. F of t as a basic signal. What all types of basic signals do you know? For example, we know unit step function. Signals are time domain. Signals are functions. So we can call them as functions. So u of n, u of t rather. See, continuous time means it is t. Otherwise, we would have represented it as f of n or x of n. But this is not of consideration because we are dealing with Laplace transform, which is applicable only for what? Continuation. That's why we consider f of t. Okay. So it is u of t, basic signal, unit step function, or unit step signal you can call. Then we have something called as unit impulse function. Unit impulse function that is represented as delta of t. Since it is represented as delta of t, it is also called as delta function. Okay. Then we can have ramp, unit ramp, which is represented as r of t. Then we can have sinusoidal functions. Understand that? Then we can have exponential functions. Sinusoidal functions, exponential functions. Understand? So we have, these are all standard signals, basic signals we call them as. Okay? Any signal that you consider in nature is the combination of one or more of such signals. One or more of such signals. Okay? So before application of or when we apply the transform, we apply the transform to these basic signals. Get that point? For example, consider Laplace transforms of, let's say, everybody just take down this, Laplace transform of some basic signals. Okay. The first basic signal that we can consider is unit step function. Let's say how unit step function looks like. See here, first one is on unit step function. It is denoted by u of t. What is u of t? U of t is actually 1, okay, for t greater than or equal to 0, and it is 0 for t less than 0. This is your unit step function. Understand? Okay, how does it look like if you plot? If you plot, it looks like this. So this is u of t now. How does it look? See here, it is 0. This is t. For t less than 0, it is 0. For t less than 0, it is 0. Okay. Then it is 1 for what? T equal to 0 or for t greater than 0. How long? Till infinity. That's why I put this dots. So what is Laplace transform of such a signal, which is 1 for t greater than 0 here, which is 1 for t greater than or equal to 0 and 0 for t less than. What is the Laplace transform of such a signal is the question. Okay, how does it look like? See here, we have to take x of s. What is x of s? X of s is 0 to infinity x of t dt, right? X of t into e power minus st dt. Okay, in place of x of t, what we can have? We can have u of t. Understand? So it is 0 to infinity u of t e power minus st dt. Isn't it? Now, what is this u of t? U of t is 1 from 0 to infinity, isn't it? See here, it's 1 from 0 to infinity. Everybody, see here, it's 1 from 0 to, so u of t is 1 from 0 to infinity into e power minus st dt. So what is integral of an exponential? It's the same. Divide, since it is being integrated with respect to t, so this minus s would come into denominator. So applying the limits is this. Okay, keep 1 by s out, 1 by minus s out, and what is application of it? It is e power minus infinity. Okay, then minus e power 0. What is e power minus infinity? Is minus 1 by s. E power minus infinity is 1 by e power infinity. Okay, minus 1. What is 1 by infinity? So this is minus 1 by s, 1 by infinity. So because e power infinity is infinity, minus 1. What is this? This is 1 by s into 0 minus 1. Understand that? So what would this be? This would be 1 by s. That means f of s, that is therefore f of s, which is Laplace transform of u of t, is actually given by 1 by s. So Laplace transform of a unit step function is 1 by s. Everybody understand? How did we do that? See here, we have to first understand what is u of t. U of t is a signal which is 1 from t equal to 0 to infinity. From 0 to infinity, it is 1. So from 0 to infinity, u of t is taken as 1. This is the formula that we need to use to find the Laplace transform and do the simple integration. Okay, and from that and applying the limits of integration, we end up getting it as 1 by s. Everybody understand that?